In this video, we're going to summarize pretty quickly what it means for a function of two variables to be differentiable. And this sort of thing, of course, as has been the trend so far, will generalize to 3, 4, and so on variables. Okay, so let's say we're talking about a function f equals f of xy, right? So a function of two variables. Right, we can define this new function h of xy as f of ab plus the partial derivative of f with respect to x at ab, that's a number, times x minus a, plus the partial derivative of f with respect to y at ab times y minus b. So those of you who remember some stuff from Calc 2, this is pretty close to the end. And I think you see this in Calc 1 a little bit. But let's stick with the Calc 2 analogy. This is the very first few terms of the Taylor series for a function of two variables. This is the degree 0 and degree 1 terms, right? So it's just the constant and the linear terms. This is one of probably 2 times you'll hear me mention Taylor series again in this class. But okay, so this is sort of the first order approximation of the function. Right? It's supposed to be a linear approximation of the function. And we say that this function f is differentiable at ab if this limit here is 0. What is this limit? Right, so it's the limit as xy goes to ab, so it's one of these 2D limits, which are a little bit trickier, remember, because there's not only a from the left and from the right, or from the right and from the left, there's also from the top and from the bottom, from the diagonals, there's from some swirling path, parabolas, there's from all sorts of things, right? So, but what it's saying is that the function should get really, really, really close to its linear approximation at the derivative if it's going to be differentiable. That's more or less what happened. Okay? And this down here acts as kind of like, the h. All right. So, well, this is usually really difficult to check because these kinds of limits are pretty difficult. So how do we check if a function is actually differentiable? Well, unless we're dealing with kind of really nasty functions, then we can usually just go with the rule that if we can write down the derivatives, then it's going to be a differentiable function. And that's supported by this theorem here. So if the partial derivatives exist, which is the sort of we can write them down part, in other words, like we can say here's a function and take its derivative, right? If they exist near here, and they have to be continuous at the point, then f is differentiable at the point ab. Okay? So, like I said, it's almost like if you can write down the derivative, if you can take the derivative of the derivatives, sorry, there's more than one, the derivatives of the function, then it's differentiable. I know that seems a bit strange to say if you can do it, then it is what it is, but this should kind of make sense, right? If the operations, if you can do them, then it should make sense that, yeah, okay, it's differentiable. I did it, see? But sometimes in math, you have to be a little bit careful with that line of reasoning. And we'll be giving you an example to show you why, that's a little bit dubious sometimes. But as long as you have something to back it up, then it's fine.